Hello everyone, in today's tutorial we are going to build a flood fill algorithm which is commonly used in the paint buckets fill method in designing tools like Photoshop, Paint and others. We are going to look at how do we implement this algorithm using the concept of graph, and we will use BFS and DFS to implement this algorithm recursively and iteratively. But before we get started, make sure you check out free masterclasses on Scalar's event page to learn from some of the best industry experts. Also, subscribe to our channel if you haven't already. Let's begin with the tutorial. So let us understand the problem statement first. So in all these designing tools like Photoshop, Paint, what do you have? You have an image and you have to manipulate pixels of an image by filling some color. So what we have to do, we are given an image. So in general, a image is represented as a grid of pixels. It's a 2D grid of pixels where each pixel represents a color, right? So that is a separate discussion that each pixel is made up of three integers, a component of red, green and blue. So effectively at the memory level, image is a 3D thing. But if you look at image as a grid of pixels, it is actually a two-dimensional data structure. For the sake of simplicity, we will represent each color by a single integer. But in actual, it's going to be a component of RGB, right? So that actually makes each image a 3D matrix. But for now, we are assuming that each color is an integer and we are representing this image as a 2D matrix. So image is represented by a m cross n matrix where image ij represents the pixel value of the image. So 1 represents a color, 0 represents another color, and so on. You are given three integers, SR, SC and color. You should perform a flood fill on the image starting from the pixel at the image SRSC. Basically, we are given, okay, you have to drop the paint bucket tool at this particular some coordinate, okay, some coordinate SRSC it is given, and it should do a flood fill. That means the color should spread in the neighboring regions which are having the same color, right? So for example, if I drop a color 2 here, so it will spread in the neighboring regions and it will make these pixels as 2, right? So this is not affected because it's also about the connectivity, how the neighboring pixels are considered. Is it a 4-directional connectivity or is it a 8-directional connectivity? So let us understand the second part of the problem statement. To perform a flood fill, consider the starting pixel plus any pixels connected in 4 directions. So basically, if this is a pixel, the neighboring pixels are top, right, left and down. The diagonal pixels are not considered as neighboring pixels. So connected to the 4 directionally to the starting pixel of the same color plus any pixels connected 4 directionally to those pixels also with the same color. Okay, if there is a pixel with color 3 here, so it will not change its color because it represents a different color, right? And so on. Replace the color of all the A4 mentioned pixels with the color. So basically, if you drop the paint bucket here, now this has a neighboring pixel, this has a neighboring pixel, this which is of the same color. These pixels will change its color. Okay, so return the modified image after performing the flood fill, right? So to make the things little more clear, I have found a visualizer on the internet that I will show you. So in this visualizer, we will draw some shape and we will try to drop the color just like we do in Paint or any other tool. So firstly, I'm going to draw some shape, and in order to draw the shape, maybe I'll choose a black color. So I have to click and I have to, maybe I'm just making some kind of a maybe apple or something, right? So let's say this is the shape I have created, right? And now I can just, what I can do, I can say, okay, I want to fill inside this shape. I will select a pixel, I will select a color. Let's say I will select the green color and I've selected the fill method. Now this is where the flood fill is going to come into picture. I'm going to maybe drop the color here, right? Now you can visualize this, all the white pixels, they are of the same color and all of them which are the neighbors, they are connected, right? If I drop a green color here, you can see this got filled. What exactly happened? It executed a DFS based algorithm. So let me show you how did it work. So I dropped the green color here. It said, okay, can I go to the left pixel because it was also white? So yes, it went and made it green, 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 green. So this way it went. Now from here, it cannot go right. So what it can do, it tried to explore, can I go to top? No. Can I go back? No. Can I go down? Yes, I can go down, right? Again, it cannot go right. So either it will go down or either it will go left. So it will happen like this. Okay, so the DFS will happen like this, and so on. And maybe then it will backtrack, it will come to this point, it will say, okay, can I go top? Yes, it can go to top. Can I go top? Yes, I can go to top. Now here I cannot go top, maybe I can go right, and so on, right? So this with this entire grid will get filled. Basically you need to decide a direction, right? So when you're making a function call, you will have follow a specific order that, okay, I will make a call to the topmost pixel. If I can go there, I will go there. But if I cannot go there, maybe it is a black boundary. So I will not go there. I will come back and I will go right. So again, recursively, you will go right. Again, recursively, you will go right, and so on. But at some point, you might come back from that branch because there is no further. So here is a boundary. So you come back. Can I go down? Yes, I can go down. I can go down. I can fill the entire region, right? But at some point, it might happen that there is a boundary here and there are no more cells available to get filled. So you might backtrack, you might come back here. And now you might explore this direction or this direction, right? So you'll follow a certain order, but irrespective of the order that you follow, this flood fill will be able to fill the entire region, right? So if you want to try out one more example, we can do that. So I'll just reload the page. I will click on draw. So I will draw a complex shape this time in which we have, let's say, two components, right? So now if I leave maybe a little bit of space here, right? Okay, now if I say, okay, I want to fill, and now you can see in this region there is no way to come. So if I fill red color in this region, maybe I will drop it at this point. This part will get filled, and there is no way for the color to leak into this region because there is no connectivity, right? So the connectivity is a four-way connectivity. If it was a diagonal connectivity, the color will also leak into this region. The red color will come into this region, right? This is how the flood fill is going to be done. And now we will look at the implementation, understand the algorithm, and implement it using DFS. Let us try to implement the flood fill algorithm, and I will explain you the steps side by side. So I've created some boilerplate code and I have made the function call. So this is the method that I would like to finish. So I'm getting the image, I'm getting XY, which is, let's say, some current coordinate, and some current color, which is, let's say, the color at XY, and the new color that I want to fill. Maybe I want to fill these ones with fives, right? Maybe I want to put 5 here. So that is maybe the new color, right? Now let us try to see what's going to happen. Let us assume that we have just one row and we have 4 pixels. So let's say this is the black color, this is the boundary, and you start a flood fill from this particular cell, and you go into 4 directions. You go right, you go down, you go left, and you go top. So when you go right, since it is a DFS call, so it will recursively make calls on the next cell. So you make this as 5, you come here, you make this as 5, you go here, you make this as 5. Now you hit this cell. Now this is of a different color, right? Maybe this is a boundary. So what you have to do, if you hit a different colored cell, you have to go back, right? Now the next direction you explore is down, but going down, it is possible that you might have array here, right? So let's say we have more cells here. So you come down, you say, okay, this is white, I need to paint it. So you put a 5 here, and again you try to go right. So you go right here. You again, it is white, so you put it 5. Again, if you go right now, what you observe, you are going outside the grid. So if you hit a cell which is outside the grid, you have to immediately come back. So you will return, right? Next direction you explore is you go down. Again, it is outside the grid, so immediately you come back. Then left. So if you see left is already painted in 5. So it is of the or this color is same as the new color that you want to paint. So again you will come back, you will not go here. And now this direction is also explored. What about top? Can you go top? Top cell is again a boundary. So what do? Now you backtrack. So you can say, okay, I'm done at this cell, I cannot do anything further. So you come back to the previous cell, which is this. Now at this cell, you have explored the direction right. Can you go down? Again, it is outside, so you come back. But can you go left? Yes, I can go left. So you explore this direction. Again, can I go right? Right is already 5, so you do not go there. So can you go down? Outside the grid, you cannot do there. Can you go left? Yes, I can go left, so I make it 5. Again, can I go right? No, it's already 5. Can I go down? It is outside the grid, so you come back. Can I go left? Again, it is outside the grid. Can I go top? So it is already 5. So it is basically checking this 5. It is serving the purpose of visited, right? So we do not want to go to that cell. So you do not need to maintain a visited array separately because the color is 5. That means we have already painted this cell into new color. So you can just come back, right? Now again, at this point, what you will do, you will backtrack. So you will go back to this cell, you will go back to this cell. From here, you will now go top, which is again 5. You will come back. And now you can see at this cell, we have visited all directions. So I'll just backtrack here. Can I go top? Again, it is 5. So you backtrack. Now at this cell also, I have visited all directions. So I backtrack, I come here, I backtrack, I come here, and so on, right? So this is how the flood fill algorithm is essentially going to work, and it is going to fill the shape in which we are putting the color. Now let us implement the code along with the various conditions. So the first condition is going to be, if I'm going to go outside the grid, I can immediately come back. So outside the grid, what you do, you have to return, right? So for that, I need to know the number of rows and columns. The number of rows will be nothing but, you can say, image dot length, and number of columns will be image of 0 dot length. So length is not a function, it is a property of array, so we can fix it. So if you have image, right, so number of rows n will be the length of the image array, and number of columns will be equal to the number of the length of the 0th row or any row, right? So that is how I know the size of the array. What will be the condition? So if x is outside the grid, so if x is less than 0, that means my row number is less than 0, or x is greater than equal to the nth row, right? Or my column number is less than 0, or my column number is greater than equal to m. So in this case, I do not need to do any work, and I can simply say return. Then what else? So if I encounter the boundary, so another condition would be, you encounter a cell of different color. So for example, you wanted to fill the cells which are 1, but from 1 you go to 2. So if you go to this cell, you do not need to change it, right? So that means if the color, if the color in the image at cell x comma y is not same as the current color, so current color is white. So if you encounter something like black or blue or green, so you do not need to change that color. So it is a boundary, right? So if it is not same as current color, then again you have to go back, so you can return, right? And there is one more case, you encounter a cell which is of new color. That means you wanted to fill 5, and the cell that you're visiting is also 5. That means basically it is the case that a cell is already visited, or by default it was painted of the same color, right? Then also you have to go back. So if image of x comma y is same as new color, then also you have to return, right? So what I'm trying to say, that you were here 5, you wanted to paint 5, you painted 5, and you made a call to the top, and it was already 5, right? So maybe you came this way, so it is already visited, it is already painted, so you don't have to go there, you just have to come back, right? If this is not the case, then in DFS what do? We iterate on the 4 neighbors, and we make the function calls, right? In this case, we have a image, we don't have a adjacency list, but what we can do, we can easily compute the 4 neighbors, right? So if this cell is x comma y, so this neighbor will be x plus 1, So I'll draw it here. So if this cell is x comma y, this neighbor will be x plus 1 y. This neighbor will be x comma y plus 1, right? And this will be x minus 1 comma y, and this neighbor will be x comma y minus 1. What do we need to do? We need to make DFS call on the four neighbors. Now you might say, okay, we checking the neighbor is visited or not? We are not checking here, but we have made a base case, right? So what we were doing earlier in previous DFS function that we had written, before making the call, we were checking that should I go to this cell or not. Now I'm going to make blind calls, but if the cell is visited, it is going to return immediately from there, right? So both the ways are correct. So either you make a call and then return, or you do not make a call, right? So here I'm going to make a call and I'm going to return from this base case, right? So now making the call is pretty simple. So I need to call flood fill method. So I'm going to give image x plus 1 y, go right, current color and new color. So I'm going to make four such calls. 1, 2, 3, 4, right? Let us update the values of x and y. So second call is I'm going to make down. So you can make in any order, that's not going to change the final output. Then I can go x minus 1 followed by y, and then I'm going to make x comma y minus 1. So this actually finishes my algorithm. So this becomes my recursive case where I'm recursively visiting all the four neighbors. So when you make this call, it's going to take you right, and eventually you come back, then you will explore this direction, right? Again, once this call is over, then you explore this direction and so on, right? So dry run, I've already shown it to you. Now we have written the code. Let us test our code on the given input. I think one important step we have missed is the actual painting step, right? So that is going to mark the cells in the new color. So let's write the painting step. Before you visit the neighboring cells, you have to paint the current pixel as well. So you will say, okay, image of xy will be now painted in the new color, right? So that is the main step of the algorithm. So yeah, this looks fine. Now we can actually run our code. So I've made the function call, and then I've written two for loops to print the image matrix. So let's go and run this code. So what is happening? I'm dropping a color 5 at cell 4 comma 4. Let's see what output do we really get. We are getting some output here. Let's try to see this output. So this is 0 1 2 3 4 in this row. 0 1 2 3 4. Basically at this cell I'm dropping a color 5. So this will actually spread color right, nothing is there. So this will get changed. So this will be 5, this will be 5, this will be 5, this should be 5, this should be 5, this should be 5. Then again we come back, we go here 5, this will be 5, this will be 5, this will be 5, 5, 5, 5, right? So yeah, I think this should be the correct output. We have 4 fives, 2 fives, 4 fives, yeah, and we have 1 5 and 2 5s. That seems correct. So basically this kind of a shape will get repainted in this color, right? So I hope you have really understood this algorithm. The code is pretty simple, and what we have done, we have simply done DFS, and we have put some conditions to stop this DFS from spreading, right? So one condition is we do not go outside the grid. Another condition is that you were filling white region, but you encountered a different color, right? So maybe you encountered a boundary. So you come back, you do not go into this region. Another is that if it is already visited, that means if something is already 5, right? Now this can happen in two scenarios. One, the image initially had 5, and second scenario, you painted that region as 5. That means it is kind of a visited region, right? So we do not do work here. Otherwise, we paint it and we recursively paint the neighboring cells, right? So I hope you really understood the DFS approach for flood fill. Let us try to understand how flood fill can be done using our BFS based algorithm. So first I will show you a visualization, and then I will do the implementation, right? So let us maybe draw a shape, okay, just a random shape, right? Let's say this is a shape, and I want to fill this with, let's say, orange color, right? So I'll just select some color, right? And the algorithm is BFS, and I want to fill. So I'll drop a color maybe here, and you will see how it's going to get filled, right? This is how it is getting filled, right? What did we observe? So we observed that if you drop a color at this particular cell, it kind of spreads to the neighboring cells, okay? And this is what we learned in the BFS, that first these cells would be covered, then further these cells are put into the queue, and they will try to traverse their neighbors. If you pop out this one, it will try to cover this. If you pop out this one, it will try to cover this, is already covered, this. Talk about this cell, it will cover this, and so on, right? So in a way it's going to be in like this order. The color is going to spread evenly in the four directions, right? So if I show you once again, if I draw maybe drop a color here, right, maybe outside, you can see it, the way it is spreading out, it is radially kind of this is how it is trying to spread out, right? Because each cell is trying to paint the four neighbors, right? Now in order to implement this, we will need a queue like we did in BFS, right? And the remaining logic, it's going to be remain similar. So I have created a one empty function flood fill BFS. We are getting the same parameters: image, xy, current color, and new color. So let us finish the code, and I will explain you the steps side by side. So first of all, what do I need? I need to implement a queue, right? So I will create a queue. So linked list class provides me with the implementation of queue. But in queue, what kind of data I'm going to push? So now each cell is represented by two coordinates, right? Basically, I need to create a pair of the coordinates to push it into the queue, right? So I have implemented a pair class where I have first and the second attributes, and I have a simple pair constructor that sets the first and the second attributes. So let us go here, right? So I would say linked list of pair. The name of the object is called queue. This is equal to new linked list. And in this queue, I'm going to initialize it with the source node. So I can say queue dot add last. It needs a pair. So new pair of x comma y, right? Now this is in the queue, right? So maybe this cell has some xy. So I push it into the queue, right? So this xy is there into the queue. So next time I'm going to pop out this node, and I'm going to traverse, I'm going to paint the neighbors which are having the same color, right? So I'm not going to paint this one, but I'm going to paint these twos because they are having the same neighbors. So I'm going to push them into the queue, right? So I can say while the queue is not empty. So while the queue, okay, it is queue, right? While the queue is not empty, what do I need to do? I need to pop out one pair. So I can say, okay, pair P, this is equal to Q dot remove first, right? So this will be pair P, right? Okay, how do I access the current cell? I can say, okay, the current X is P dot X, P dot first, pair has these two attributes. Current Y, the current Y that I've popped out from the queue. So it's going to be P dot second. Now what you need to do? You need to paint this cell. Okay, you need to paint this cell. So painting means we are kind of marking this as visited. So I can say, okay, image of cx and cy, this will be marked with the new color that I'm getting. So I basically change the color, right? Now of course I have to find out the neighbors. Basically I need to find out the 4 neighbors and push them into the queue, right? Push them into the queue. Now in case of recursive, we can just make a call on the neighbor and we can return, but since it is a iterative algorithm, we cannot push every neighbor into the queue. We have to take care of conditions, right? Now suppose this is the cell and this is outside the grid, so I do not need to push this neighbor. Now suppose this is the cell, this cell is having a different color, so this is black. I cannot push this neighbor into the queue. Maybe this is open, this was one, this was one, and this was one, right? So in such a scenario, I just need to push this one and this one into the queue because it is having a different color, right? So I cannot push this one, right? So I update the color of this maybe to 5 and I will push these two into the queue. Next time we will pop them out and they will try to cover their neighbors, right? Okay, so something like this it's going to happen. So now how do I find out the 4 neighbors? Of course, one way is we can just hard code the parameters here, right? Or other ways I can use a loop as well, right? So personally, I like writing the loop. So I've not shown you the loop in this one, but we could have done a loop here as well. So how do I write a loop? So basically, you have to think of 4 directions, right? So if this cell is xy, so what is happening here? So the x is getting incremented by +1. Here the x is same. Here x is decremented by -1 and here x is same, right? So if I look at the delta change in x, right? So I'm going to create a array here, delta x, right? So delta x is going to be like 1 0 -1 0, right? So I'm writing in this direction, right? What about delta y? So in this direction y is not changing, so delta y is 0. If I go down, the y is incremented by 1, right? And if I go here, the delta y is still the same, and if I go to the top, the y is getting decremented by -1, right? So the change in y is 0 1 0 and -1. So I'm going to create a delta y array. So it's going to be 0 1 0 and -1. Now you might ask, where do we need this array? So this is going to be helpful. Now suppose if you want to go into this direction, you can say okay, x plus delta x of this direction. So let's give this index 0 1 2 and 3. So these are 4 directions, right? So delta x of 1, basically x will be incremented by 0, and if I go down, y will be incremented by delta x of 1, right? So first direction, right? So y will be incremented by 1, right? So instead of just hard coding the 4 things, we have summarized them here, right? Now how do I find the 4 neighbors? Pretty easy. I know there are 4 directions. So I equal to 0, I less than 4, I plus plus, right? So what is the neighbor of x? So neighboring x is nothing but current x plus delta x, how much I have to change, right? Similarly, neighboring y is nothing but current y plus dy of I, delta y of I. So this is my neighboring x, this is my neighboring y. So I got the 4 neighbors. Now there are conditions on these neighbors we need to impose. This neighbor should not be outside the grid, or I want to push this neighbor if it is inside the grid and it is having the same color as the current color, right? So what is the condition to push? If this is a cell, right, x comma y, this is of a different color, this is outside the grid, this is inside grid. So this is neighbor, this is neighbor, this is neighbor, this is neighbor. So I cannot push this, I cannot push this, but I can push this, I can push this. So the condition is it should be inside the grid and it should have the same color as the current color, right? So I can say okay, if x is greater than equal to 0 and x is less than n and y is greater than equal to 0 and y is less than m. Okay, I need to define n and m as well. So and they should have the same color, right? So if it is white, I want to have it as white. Only then I can paint it. So I can say okay, image of neighboring x comma neighboring y. Actually this will be nx and ny. Actually neighboring x, we are talking about neighboring y and neighboring x. Yeah, neighboring y and image of neighboring x and neighboring y, the color is same as the current color, only then I need to push it. So I can say q dot add last new pair of neighboring x and neighboring y. So I need to define n and m. So n is image dot length and my m is going to be image of 0 dot length. So I think this completes our BFS. We have traversed on the neighbors and the valid neighbors they have pushed into the queue, and this we are doing while the queue is not empty, and here we are painting the cell, right? So this will traverse all the neighbors which are of same color, right? And let's try to run this code now. So earlier I had done the DFS call, now I'm going to do the BFS call with same parameters, and let's see do we get the same output or not. Ideally we should get the same output. So if you look carefully at this shape, so I dropped the color 5 at this cell maybe. So this whole component should become 5, and even this one also, right? So this should become 5. Let's see, are we getting the same shape? Yes, we are getting the same shape, right? So you can see how this flood fill is working, right? So while we are getting the correct output in this case, but there is one problem with this algorithm that I'm going to show you. Let us try to understand what is happening when we are doing this BFS. We started with this node, this particular cell. We pushed this into the queue, the corresponding um, coordinate. Okay, let's say the coordinate is A. So I pushed this A into the queue, right? Next time I removed this, I painted it 5. Okay, so marking this means painted it 5, and I pushed the neighbors. So neighbors which are of the current color. So this 2 and this 2, only these are the two neighbors. Let's call it B and let's call this neighbor as C. So I pushed the neighbors B and C into the queue. Next time I removed B, I painted it 5 and I again pushed the neighbors into the queue. Let's say this neighbor uh, D and this neighbor E. So D and E, they are also pushed into the queue. Next time I will remove C, right? I will remove C and I will again push the neighbors. Now one neighbor is this. I will of course paint it. One neighbor is this, and but this is already into the queue, right? And this is also going into the queue. What is going to happen that some neighbors like this node, they will be present into the queue multiple times, right? So if you do not believe me, I will show you. So I have written a statement that okay, while the queue is not empty, I'm going to remove a particular cell. So if we get the same coordinates again, that means a particular cell has been pushed into the queue multiple times in this algorithm. So we need to fix that, right? So removing 4 4 5 4 3 4 4 3 5 5 5 3, okay, 3 3 3 3, right? Look at this 3 3. So this 3 3 is present into the queue two times. What is this coordinate 3 3? Let me show you. This was 4 4, right? No, 0 1 2 3 4. Okay, this was 4 4, right? 0 1 2 3 4, right? So it might have discovered this, basically this cell, right? So it was entered by this neighbor also, this neighbor also. We want to avoid this, right? So in order to fix this, we need to go with the visited array thing, right? So like in BFS, we do maintain, okay, whether a node has been visited earlier or not. Same thing we have to maintain here as well. What I need to do, I need to maintain a boolean visited array. So this part I can move a bit here, and I can say okay, I'll need a visited array. So boolean visited equals new boolean of the size n cross m. By default everything is false in Java, so we don't need to set false. Then when you're adding the first node, you can mark this as visited. When something goes into the queue, you have to mark it visited. So visited of x comma y, this is equal to true, right? And then when you're pushing again something into the queue, you have to say visited of x comma y, this is equal to true. And then again when you're checking that should I add this cell into the queue, so you should add if it is not visited. So not visited nx and ny. So here also it will be nx and ny, the neighboring x we are talking about. So I think this now is close to the actual BFS logic that we have implemented. This visited thing is important. I've shown you why. And now there are three conditions here, right? I think this, it's better to put it here. And ny is less than m, and not visited nx ny, and image color is equal to current color, right? So three conditions now: visited, color condition, within the bounds, right? Now let us run this code, and now we should not see duplicate cells here. 445434, 43555333, 655632753176. Are we still getting the same output? Yes, we are still getting the same output, and this is the correct way to implement the algorithm, right? So I hope now you have understood the importance of visited array and the implementation of flood fill using BFS. So that's the end of this tutorial. I hope you learned a lot of concepts. So if you like the lecture, please make sure you like the video, share it with your friends, and subscribe to our channel for more such amazing tutorials. Thank you, and I will see you next time.